Okay, so here's where we were last time. We were talking about rearrangements of blocks inside a Jordan canonical form. Now remember, we spent a bunch of time talking about what does Jordan canonical form even mean, right? And it's a list of rules. It's got that in common with reduced row echelon form. Reduced row echelon form is a bunch of rules about increasing numbers of leading zeros and pivots being one and what else can be in a pivot column and all that kind of business. So just a bunch of rules defining the structure. So likewise, Jordan canonical form is just a structure. Okay. The structure, of course, consists of a bunch of blocks, and we talked about, what's in the various blocks and how they relate to each other last time. So, by rearrangements, we noticed last time that if you have a matrix, a Jordan form matrix, that represents some linear transformation T with respect to a certain basis, if you simply reorder the vectors in the basis, so don't change any of the basis vectors really, just kind of move them around, right? To get a new basis of, again, same vectors, just in a different order, then you can compute the corresponding matrix, and in this case, we got another Jordan form matrix, right? So there's a sort of an unhappy conclusion of this, and that is that Jordan form is not unique, right? So you can immediately see that this linear transformation T, there's more than one Jordan form for it, right? That form up there is a Jordan form. This form down here is a Jordan form. They represent the same linear transformation, just with respect to, I'll call them different bases. So Jordan form is not unique. However, these two Jordan forms do pretty clearly have something in common, and that's this rearrangements idea that we came up with. These blocks are just the same blocks, just kind of rearranged along the diagonal. So let me make that a little bit more explicit. So notice this basis here. We started off with vectors v1 and v2. As part of the reordering, those moved over to the end. There was v3 in the third position, that stays in the third position. And then there was V4 and V5 that were at the end and that are now at the beginning. So you can see there's a sort of a method to the reordering. This is not just a random reordering. And notice that this first block here, well, that first block, let's see, that first block corresponds to first and second rows and first and second columns in a way, then, kind of corresponds to the first two basis vectors. And you could reasonably speculate that in the same sense that those first two basis vectors move to the end, that's why the block correspondingly moves to the end. Right? And then likewise, the third basis vector corresponds to third row, third column, namely that block, and it stays in the third position, so that block stays third row, third column. Likewise, this V4 and V5, fourth and fifth row, fourth and fifth column, that block moves to the first and second position, so first and second rows, first and second columns, namely that position. So, as it happens, this particular reordering of the basis vectors gave rise to a corresponding rearrangement of the Jordan blocks. So, interesting how that worked out. Yeah.
What would have happened if, V5 got split up?
Yeah, that's a great question. So that's one of the next things I was going to talk about. So, it is not true that this will always work out so nicely, right? It is not true that every single reordering of a basis will merely shuffle Jordan blocks. It's not the case, right? So per your question, so he asked, well, what if you had taken the V4 and the V5 and split them up, maybe, and along those same lines, what if you took the V4 and the V5 and switched them around like that? And the answer is that the resulting matrix simply won't be in Jordan form at all. Right, so I'm not suggesting by this example that every reordering of the basis will simply rearrange blocks. What I am kind of suggesting by this example is that however you might want to rearrange the blocks, think about how that rearrangement of blocks would correspond to reordering, let's say, columns, and a corresponding reordering of the basis vectors will accomplish that rearrangement in question. So every rearrangement can be accomplished with a reordering of the basis vectors. Now, how does this rearrangement work? I mean, how do we get from there to there? We talked about this last time. We talked about this column here. That column tells us ultimately T of V2 is equal to 1V1 plus 2V2. Right? This is a matter of interpreting, correspondingly from, this matrix and what it represents. It represents T with respect to the script V basis. It's the second column, so it tells us about T of V2. It tells us about T of V2 by these being the script V coordinates of T of V2. Or said differently, T of V2 is that linear combination of the script V vectors. So, that equation. Well, what we observed last time is that this column says the exact same thing. I mean, this is the fifth column, so it's telling us about the image of the fifth basis vector, but the fifth basis vector is V2. Right? And it's telling us T of V2 as, being this different looking linear combination of the W basis vectors. There's a bunch of zeros at the beginning, right? But when you start reading it off, we have 0V4, 0V5, 0V3 from these zeros here. And then 1V1, 2V2, the same equation. Okay, so exercise that I'm going to leave for y'all is to write down all 5 of the equations that are represented by this matrix, understanding it as representing T with respect to the W basis. Write down all 5 of the equations represented by this matrix, understanding it as telling you T with respect to the script V basis. And then just observe it's the exact same 5 equations, just written down in a different order, and with the terms inside of each equation written down in a different order, but ultimately it's the exact same 5 equations. Okay. All right. There's a different point of view that you can take, and I encourage you to play with this one as well, and that is to notice that if you simply reorder basis vectors, this matrix turns out to be a special matrix. The change of basis matrix from one basis to another, where these bases are just reorderings of each other. It's a permutation matrix. It's a matrix that's all zeros except for a few ones, where there's exactly one one in each row and exactly one in each column. And it corresponds to just shuffling things that it does stuff to. So so this being a change of basis matrix, when you do the change of basis on the linear transformation, when you convert with that permutation matrix, when you convert that to that, keep in mind there's a conjugation. So you're going to multiply this change of basis matrix on the left here. That's going to shuffle the rows. But then you're also going to put its inverse on the right. That's going to shuffle the columns. Effectively, you're shuffling the rows, shuffling the columns, and that will achieve the same end of rearranging the blocks. Okay. All right. So, what's the upshot here? A quick reference. There's an additional homework problem that's heavily modeled on this example. It's just going to have you do for a different example, roughly speaking, what we've talked about here on this example. Okay. So here's the punchline from the previous example. All rearrangements of a given Jordan form, by which I mean, if you have a Jordan form, if you look at these blocks, and if you just say, I want to move these blocks around in some way, all those rearranged Jordan forms, they're all similar. They all represent the same linear transformation, and they all represent the same linear transformation just by, just reorder the basis vectors accordingly. However you shuffle the blocks, just shuffle the basis vectors the same way. Okay, so all rearrangements are similar, yeah. Yep. So similarity, there's 2 different ways you can think of similarity. One way to think of similarity is by a conjugation. And another way to think of a similarity is that the 2 matrices represent the same linear transformation just with respect to different bases. Right, so a change of basis point of view on similarity. Yep. Okay. Erase all this junk here. Okay, so all rearrangements are similar. Let me say that a little bit differently. If you give me two Jordan forms that are rearrangements of each other, they are similar to each other. Okay, and that's just a matter of looking at how the algebra works in that previous example. I think it's a pretty plausible conclusion. This theorem, not as obvious by quite a bit. This is a much harder theorem to prove. We're not going to prove this in Math 216. And it says sort of the opposite. It says that if you give me two Jordan forms that are similar, they are in fact rearrangements of each other. In other words, rearrangements are the only different kinds of similar Jordan form matrices. So any two Jordan form matrices, if they're similar, they have to be rearrangements of each other. And saying it just a slightly different way, if you kind of ignore rearrangements, if you sort of say, look, rearrangements, they're just similarities. We're trying to represent an equivalence class of similar matrices. So anything that's similar we don't really care about. So we already know rearrangements are similar. So let's ignore rearrangements. With that understanding that we don't care about rearrangements, there is exactly one Jordan form. So this is a kind of a recovery. You know, the very first thing that we said at today's class was that, okay, well, the obvious conclusion here is that Jordan form is not unique. Look at that. Here's two Jordan forms representing the same T. Clearly, Jordan form is not unique because those matrices are similar to each other. They're conjugates of each other. They're change of bases of each other. The recovery is saying, okay, yeah, but these are similar in a sort of an obvious way with the rearrangements. And for reasons that, again, are beyond Math 216, that's the only kind of similarity there is between Jordan forms. So with the understanding that, of course, yeah, you can rearrange, with that understanding, Jordan form actually is unique. Okay, so nice conclusion. It allows us to address this example down here. Here we have two Jordan forms. Let me illustrate what we've got here. There's a single eigenvalue block there with two basic Jordan blocks, like so. And on the other hand here, one eigenvalue block and one basic Jordan block. So we have here two different Jordan forms. And let's ask the question, might it be possible that maybe these Jordan forms could be similar to each other? Maybe these could represent the same matrix, some other matrix. Maybe they represent the same linear transformation. Answer, no, not possible, because they're not rearrangements of each other. The theorem above says that rearrangements are the only similarities between Jordan form matrices. And these are obviously not rearrangements of each other because the blocks are just different. Different blocks. They're not the same blocks in different places. They're different blocks. How are we doing? Everybody on board? Okay, there's another thing I want to talk about now. I kind of glossed over something when we were talking about the structure of Jordan canonical form. Let me remind you. We talked about the eigenvalue block structure. This is the large-scale structure of the matrix, and we have these big blocks here called eigenvalue blocks. At least that's what I call them. Eigenvalue blocks. And we call them eigenvalue blocks because they have so much to do with eigenvalues. And we made this connection that this diagonal entry, this shared diagonal entry there, that's the eigenvalue corresponding to that block. And the dimension is the multiplicity. So there's a tremendous amount that we saw that eigenvalue blocks have to do with eigenvalues. And then when we looked inside of eigenvalue blocks, we got to basic Jordan blocks. Here's our eigenvalue block, inside of which we have these little basic Jordan blocks. And the natural question that comes up is, what do those relate to? Do these somehow relate to something relevant to diagonalization, maybe, something like that? And we punted. Right? And I made the observation that, well, there's a long conversation there, and we'll have to talk about that later. And here I'm going to come back and fill in that blank. So what these basic Jordan blocks inside of here correspond to is ultimately pretty natural. And so I want us to see that now. Okay, so let's see here. I'm going to come down to here. Let me remind you that when we're talking about Jordan form, we're talking about representing our transformation with respect to a basis. You might have noticed that, a discussion of that basis has been absent. What's inside of that basis? What kind of vectors are these? Haven't said anything so far. I'm going to give them a name here. I'm going to call these the Jordan basis, or I should say a Jordan basis. They're not unique. Yes. Thank you for the reminder. I can't seem to remember that. Ready to go there? Too late. Yeah. Okay, so I'm going to call this a Jordan basis. So it's not unique, by the way. There's lots of different Jordan bases that will put a matrix into the same Jordan canonical form. We're not going to worry about that very much in this class, but just for the record. So these vectors here, what can we say about them at all? And let me remind you, we already know a bunch of stuff about these vectors from section 5.3. Keep in mind what the matrix is. The matrix, the Jordan form, is representing T with respect to a basis. And we know that the columns are the images of the basis vectors, right? Old 5.3 interpretation. So this column here, for example, that column, if this is the ith column, is telling me about T of VI. It's T of the ith input basis vector. Okay, yeah, but it not just arbitrarily. It's giving us T of VI with respect to the output basis. In this case, also script V. So these columns are telling us about T of VI in terms of script V. As said differently, it's telling us about T of the V vectors in the language of the V vectors. And it's doing so, again, in the 5.3 sense. Let's just write down a couple of examples. Here's a basic Jordan block. I want to focus on any single basic Jordan block here. Keep in mind, if we're in Jordan form, this is a basic Jordan block. The other blocks are going to be like up there and down here and that sort of thing, and none of them will overlap with these columns. Right? The columns that overlap one block can't overlap any of the other blocks. So if I want to understand, what do these columns tell me, the columns corresponding to one block, I can just ignore all the other blocks. And by the way, what I have here, chock full of zeros. I know from the rules of Jordan form that everything outside of the block is zeros. So everything above, everything below, that's all zeros. Furthermore, everything up here is all zeros, and everything down here, all zeros. Right? The only non-zero entries in a Jordan form inside of a basic Jordan block are an eigenvalue along the diagonal and a 1 just above the diagonal. That's it. Everything else is zeros. Okay, so that being the case, let's look at one column at a time. Keep in mind that the columns are telling me about the images of the basis vectors. And let's look at this first column. Okay, that first column. Let's see here. This being as it is the first column corresponding to this block, there's only one entry in that column. That's the diagonal entry. Everything else is below that diagonal entry. That's all zeros. Up here above the block, all zeros. Down here below the block, all zeros. So all I have in this ith column is I have a lambda in the ith position. That's it. And as such, I draw this conclusion. This is the ith column, so it's telling me about T of VI. Right? It's 0v1 plus 0v2 plus 0v3 plus 0v4, etc., etc. Now, there's a lambda in the ith position, so that means I'm going to have lambda vi. That's what I have here. But then after that, 0 vi plus 1, 0 vi plus 2, all zeros after that. So altogether, I just have the one thing there. T of vi is lambda vi, which, by the way, tells me that vi is an eigenvector. Isn't that nice? Okay, cool. Let's take a look at another column. Let's look at not the first column. So any of these other columns. Now, I have an observation to make about these other columns. The observation is that because they're not the first column, because they were a little over to the right, there's going to be a 1 just above the diagonal. Now, the first column, not so. Right? The first column, there is no 1 above the diagonal because there is no position at all above the diagonal. The diagonal is the top in the left column, but it's in the top row, so there is nothing up above it at all. But all these other columns have a 1 just above the diagonal. So, for example, let's look at that one. There's that lambda on the diagonal. This is on the diagonal in the jth column. So there's a lambda in the jth position. Right, but in addition to that, there's also this 1 right there. So a 1 in the j minus 1 position. Well, that 1 in the j minus 1 position gives me that term, and the lambda in the jth position gives me that term. Let's take a pause on this for a moment. Is everybody following my algebra there? So again, this green column, that's telling me about, let me highlight here. This green column is going to give me this green equation. This is the jth column, arbitrarily, I'm saying, so it's telling me about T of Vj. There's only 2 non-zero entries. All these other entries are all zeros. So what these numbers are, 1 in the j minus 1 position gives me that term. Lambda in the jth position gives me that term. It's a straight out of section 5.3 interpretation of what does it mean for a matrix to represent a linear transformation. I'm just applying that 5.3 idea and sort of combining it with what do I know about the structure of a basic Jordan block. Okay. And I claim there's a punchline on this. The punchline is that this corresponding basis vector is not an eigenvector. Because look at this equation. Right? If Vj were going to be an eigenvector, I would need for T of Vj to be a multiple of Vj. But sadly, T of Vj is a multiple of Vj plus something that's definitely not a multiple of Vj. And that adds up to not a multiple of Vj. So Vj is not an eigenvector. Okay. All right, so reminder. That first column gives me an equation that tells me that one of the basis vectors is an eigenvector. All the others, right, all of the rest of these are telling me that certain basis vectors are not eigenvectors. Now, don't misinterpret what I'm saying here. We are not saying that this column is the eigenvector. Not at all. Right? The column itself just tells me the equation. The column tells me how the image of Vi relates to other vectors including VI, and that's what allows me to conclude VI as an eigenvector. But this is just telling me the equation. It's not telling me what VI itself is equal to. VI could be who knows what. No idea. Okay. All right, so nice little conclusion that we get here. Anytime you have a basic Jordan block, this following pattern is always going to hold because of what we just talked about. Anytime you have a basic Jordan block, that basic Jordan block will correspond to certain Jordan basis vectors. It'll correspond to some subset of your Jordan basis. Whichever is the first one, whichever basis vector corresponds to the first column that block overlaps, that one's an eigenvector. All the rest of them, not eigenvectors. Everybody happy? So now another thing I'm not going to prove is that this actually is representative of all of the eigenvectors. So not only does every block give me exactly one eigenvector, but this will give you a complete count of all of the eigenvectors. And so I'm going to state this as a theorem, and that is the grand total number of eigenvectors is equal to the number of basic Jordan blocks. And they will correspond exactly per the pattern on the previous page. For every Jordan block, there is an eigenvector. And that's all of the eigenvectors in the usual linear combinations sense. Okay, like I said, hard to prove. We're not going to prove this in Math 216. Okay, so an example. Let's look at this matrix here. And let's highlight what the Jordan form is. Here's the first eigenvalue block. Here's the next eigenvalue block. Here are the basic Jordan blocks. Right? And let's think about the eigenvalue of 4. The eigenvalue of 4, the eigenvalue of 4 has 2 eigenvectors. And I know it has 2 eigenvectors because that eigenvalue block has 2 Jordan blocks. Right? 1, 2 Jordan blocks corresponding to that eigenvalue, so 2 eigenvectors for that eigenvalue. Okay. Likewise, down here, the eigenvalue of 3. Well, the eigenvalue block has exactly 1 Jordan block, therefore there is exactly 1 eigenvector. Okay. All right, the next example just fleshes that out a little bit more explicitly. So here we have a matrix with a single eigenvalue block. Single eigenvalue block. The Jordan blocks, again, Jordan blocks are like this. Right, so 2 blocks means 2 eigenvalues, but let's find exactly what are those eigenvalues, and let's just sort of see it a little bit more explicitly. Here we go. So looking at these columns, keep in mind that first column is telling me about what the linear transformation does to the first basis vector. And you can look at that equation, again, 4, 0, 0. What the linear transformation does to the first basis vector is, well, I get the 4, 0, 0 linear combination of basis vectors. So I get 4v1. So AV1 is 4v1 eigenvector. Right? Likewise, for this one, right, that column tells me this equation. And that tells me that V3 is an eigenvector. Note that in both cases, these are basis vectors that correspond to the first column overlapping the corresponding block. Right? The first column that overlaps with the first Jordan block is the first column overall, which corresponds to the first vector eigenvector. The second Jordan block, the first column that overlaps with the second Jordan block, is the third column. The third column is telling me about the third basis vector eigenvector. So V1 and V3 are eigenvectors. I emphasize, A very common mistake. Lots of students make the following mistake, to think that what that first column tells me is that V1 is equal to 400. And it's not, right? The 400 is not telling me V1. The 400 is telling me an equation involving V1. It's telling me that V1 is an eigenvector. It's not telling me what V1 is at all. Okay. Everybody happy? Okay. All right. So there's a lot of stuff that, again, we can't do with Jordan form. The theorem that says that every matrix can be put into Jordan form is hard. We're not going to prove that in this course. I'm just going to assert that that's true, and I'm not going to prove it. Likewise, the theorem that says that all similar Jordan forms are rearrangements of each other. That up to rearrangements, Jordan forms are unique. That's a hard theorem to prove. We're not going to prove that in Math 216 either. Here's another thing we're not going to do. I'm not going to give you a general method that will always allow you to find a Jordan basis. That's hard. It's pretty hard. That's well beyond what we could realistically do in Math 216. So now we're going to get lucky in a couple of cases. We'll be able to, in certain instances, find what the Jordan form is, find maybe even in some cases what the Jordan basis is, or a Jordan basis. But as a general technique, it's not something we can realistically do. Okay. All right. So first example along these lines, note that diagonal is Jordan form. It's a special case, but it totally works. So, for example, if you think about this, here's a diagonal matrix, right? 0, 0, 0, 0, 0, 0. That is a Jordan form. Now, I did, of course, group these eigenvalues together. But there's the first eigenvalue block. Here's the second eigenvalue block. And the basic Jordan blocks are all one by one basic Jordan blocks. So, diagonal, well, let's say it this way. If the matrix is diagonalizable, then its Jordan form is diagonal form. Okay. So there, by the way, we do know how to find the Jordan basis. The Jordan basis is the basis that puts us into that Jordan form. It's the basis that puts us into the diagonal form, namely, it's the basis of eigenvectors. The eigenbasis. Okay, so like I say, every so often, sometimes you get lucky. Here's another example. Suppose you know this about your characteristic polynomial, and by the way, that's a pretty easy conclusion to draw. You're given a matrix, you know how to find the characteristic polynomial. There you go. That alone tells you a lot of information about the Jordan form. Don't forget, way back here at the beginning, way back here, there you go, the eigenvalue block structure you can read straight off of the characteristic polynomial. If you know the roots and multiplicities of your characteristic polynomial, that is, if you know the eigenvalues and the multiplicities of those eigenvalues, then you know how big are your eigenvalue blocks and what's on the diagonal in those eigenvalue blocks. Okay, so in this case here, this tells me we have a 2 by 2 eigenvalue block with ones on the diagonal. And there's only two possible such forms. You sort of think it through. What other possible Jordan blocks could you possibly have inside of a merely 2 by 2 eigenvalue block? I mean, 2 is a small number, right? There's only so much that'll fit inside of there. So these are the only two possibilities. Either you have two 1 by 1 blocks, or you have a single 2 by 2 block. Nothing else makes sense. Okay, likewise, this factor tells you have a 1 by 1 eigenvalue block with 3 on the diagonal. And of course there is only one such thing. So we've narrowed it down to two possibilities just by looking at the characteristic polynomial. I don't even know the eigenvectors yet. Right? The characteristic polynomial itself tells me almost everything that I need to write down in Jordan form. Now, okay, how do I tell one or the other? Right? Well, think about the eigenvectors. There's a couple different possibilities. One possibility is, suppose I find two eigenvectors for the first eigenvalue. Well, two eigenvectors would mean I would need two basic Jordan blocks inside of that eigenvalue block corresponding to that eigenvalue. If you find two of them, you got two blocks. That means that's not right. Ergo, it's got to be this one. Process of elimination. Right? Likewise, another possibility. Suppose when you go through and you find your eigenvectors, maybe there's only one for that first eigenvalue. Well, then there's only one basic Jordan block, and therefore it's got to be that one. So, calculations that we already know how to do will allow us to deduce what the Jordan form is for a matrix like this. How are we doing? Now, I'll confess that this does not always work, and in fact, it usually doesn't work. One could argue we're taking big advantage of the fact that we're dealing with small dimensions here, right? I mean, 2 by 2. 2 is a small number. There's only so much that can fit inside of a 2 by 2, and so we narrow down the possibilities dramatically, and then the process of elimination, in some sense, can't lose, right? But if you have a 16 by 16 eigenvalue block, and you find 9 eigenvectors, oh my gosh, there's lots of possibilities, right? And in that case, you could not deduce what the Jordan canonical form is. You have a much more difficult problem beyond Math 216, what we could reasonably do. Okay. All right. This next observation is just sort of taking what we did in the previous example to the sort of the next level. So suppose suppose that your characteristic polynomial is that. How many different possible Jordan forms are there? There's quite a few. And we can enumerate those different possibilities. Let's think about this first factor. This says we've got a 4 by 4 eigenvalue block with eigenvalue 7. And inside of that 4 by 4 eigenvalue block, let's just think about what are the different possibilities, what are the different Jordan structures that there could be inside of here. Well, there could be, I suppose, a single 4 by 4 Jordan block, or maybe there could be a 3 by 3 and a 1 by 1, or also possible there could be a 2 by 2 and another 2 by 2. Or I suppose it's possible there's a 2 by 2 followed by a 1 by 1 and a 1 by 1. Right? Now, what's going on with these equations I keep circling over here on the left? Notice that however I partition the Jordan structure into blocks, I'm effectively partitioning the columns. Right? These 4 columns, this Jordan block structure is partitioning the 4 columns into, well, there's 2 associated to that block, followed by 1 for the next block, followed by 1 for the next block. In grand total, that's 4 columns. So that eigenvalue block structure, or Jordan block structure, corresponds to the fact that 4 is equal to 2 plus 1 plus 1. Okay, so we can reduce the question of, how many different structures are there inside of here to the question of how many different ways are there to add up positive integers to get 4. Right? And these are all the ways that you can do it as it happens. There's 5 different ways to add up positive integers, not worrying about the order, right? To get 4. This is called the partition function. It's a really interesting function. It's a harder function to understand than you would expect at a glance. But the number of ways to take some number n and represent it as a sum of positive integers, ignoring rearrangements, difficult function to understand. But for low values, like, for n equals 4, it's no big deal. You just enumerate. Can't think of any other ways to do it, so that's it. How we doing? Everybody on board? A little cultural note. The partition function this thing for which this is an example, was studied heavily by this mathematician named Ramanujan. How many people have heard of Ramanujan? A few, not very many. Okay. There's a Hollywood movie that came out like a year ago about Ramanujan, because his story is unbelievable. It's kind of Good Will Hunting. Did y'all see Good Will Hunting, or does that predate you guys as well? How many people have seen Good Will Hunting? Okay, all right, that's good enough. Okay, so that was a big movie when it came out, and the idea of the movie, for those who haven't seen it, is that this guy who's a janitor, he's just a janitor, and turns out, oh my gosh, he's the most brilliant mathematical mind that anyone's seen in forever, and he's able to solve super difficult problems that even the professors at MIT can't solve, and he's this phenomenon. And he was a janitor, right? Okay, so that was not Hollywood creativity. That's modeled on the life of Ramanujan. Ramanujan grew up in rural India with no education to speak of, and managed by a stroke of good luck to just get a hold of a math book. It was not a textbook. It was kind of more of an encyclopedia. It was just a list of true statements about very sophisticated, high-level mathematics. And so here he is, poor guy, no training, no one to guide him. All he has is this book that just asserts statements about math. And he just figured, okay, I guess that's how you do math. And so he started looking at this book and thinking about these equations, these very sophisticated, abstract equations, and just kind of got it. Just kind of, okay, I see that, right? And he started coming up with his own stuff. And he was right for a very large number of the equations he wrote down. So he wrote down these unbelievably insightful, complex equations out of nowhere. He just dreamed it up. Again, no training, just on his own. And then he, sends a list of his work to various mathematicians around the world to see if anyone would appreciate it. Most of them had no idea what it was. They thought he was just a crackpot. But a professor in England, Hardy, realized who he was and what he had done, brought him to England, and there's a whole rest of the story after that. But anyway, he was it was an amazing story that someone could come out of nowhere like that. Anyway, the partition function is something that he spent a bunch of time studying, and he did amazing things with the partition function. So, all right. Okay. We're going to move on and talk a little bit about Chapter 9 now. You'll notice that we're skipping Chapter 6 for the moment. Chapter 6 is differential equations. It's another category of differential equations. I want to finish the linear algebra of the course before we go into the differential equations, so we'll be fully armed. The book makes a different choice, which is fine, but I feel that there are some aspects of Chapter 9 that are going to be kind of useful, kind of convenient when we get around to solving the differential equations in Chapter 6. So I'm going to do it in this opposite order. Okay. And we're going to start off with a new abstraction called inner product spaces. So let me remind you what an abstraction is. Y'all remember vector spaces. I hope you remember vector spaces. Let me remind you what the point is with vector spaces. Being an abstraction, the whole point is that we don't say what the objects inside of a vector space are. Right? We define vector spaces only based on how these objects relate to each other, how they behave, what algebraic properties do they have to have. But what they actually are, no comment. Could be anything. Right? We're being deliberately vague so that our construction will apply as broadly as possible in ways that we haven't even anticipated, hopefully, fingers crossed. Right? And that happened. Right? So in Chapter 2, we made this hands-off, sort of abstract discussion of vector spaces, and then it turned out that when we started studying differential equations in Chapter 4, well, lo and behold, these things, oh my gosh, look at this, they're vector spaces. Who saw that coming? We have vector spaces that we need to understand, and then all of the theorems that we developed about vector spaces, bases, independence, span, dimension, related theorems about all of these objects, all of those theorems we had to work with, and that allowed us to solve differential equations. Okay, so this happens a lot in math, that we define an abstraction, no idea what it's going to apply to, Just let's create an abstract construction, and then some later time you find that, oh my gosh, this is exactly what I needed. Okay, so that's going to happen again here, by the way. Okay. So the big idea is to take advantage of the dot product in Rn. Let me remind you again, with vector spaces, we notice certain things about Rn. We notice that Rn has an addition, it has a scalar multiplication, and there's a bunch of properties that relate these two operations to each other. So the addition and the scalar multiplication behave in certain ways. We defined a vector space to be something ambiguous, no comment, but where these operations behave in those particular ways. What we're going to do with an inner product space is just notice that there's more algebraic structure in Rn that we kind of forgot about when we were doing vector spaces. There was no discussion of dot products, you might have noticed, when we were doing vector spaces. There is no dot product in a vector space. It's not a thing. Inside of a vector space, addition, scalar multiplication, that's it. Okay. So what if we try to generalize the idea of a dot product? So, quick reminder, Math 212, there's a dot product, easy formula. Here are some facts about the dot product. Those are easy to confirm. Make sure to remind yourself of these properties. I think they're pretty straightforward, pretty easy to persuade yourself. Quick comment, the book kinda blows it on the fourth property. The book does not, the book writes down a fourth property that's not equivalent to what I've written down here, and the book's property is weaker than this. The book's property is weaker in a way that's going to matter. So the book's property is not quite strong enough to be able to do what we need inner product spaces to be able to do. So we're not going to do it the book's way, we're going to do it my way. Note my property a little bit stronger than the book's fourth property. Specifically, the book allows a dot product of a vector with itself, or the book's observation about the dot product is simply that it's only zero if V is the zero vector. They don't explicitly note that this is never negative. They just don't note it, and we need to note it. Okay. We'll see more about that later on. Okay, so there's several other properties about the dot product, and again, I hope these are all familiar. If you're a little rusty on your Math 212, this would be a good time to brush up. But these are all true facts about the dot product. But we're not going to focus on those right now. We're just going to focus on these four, and we're going to, just like we did for vector spaces, we're going to say anything that behaves like this is, in a sense, kind of like the dot product. Right? So, again, when we were talking about vector spaces, we wrote down 8 conditions and said that anything that satisfies these 8 conditions, those operations behave kind of like Rn's addition and kind of like Rn's scalar multiplication, and so we're just going to say, look, that's kind of like Rn in that sense. We'll call it a vector space. Anything that behaves like this, by analogy, we're going to say kind of behaves like the dot product, and the name we give to it is an inner product space. So here's the definition. We start with a vector space. So we've got to have addition. We've got to have scalar multiplication. They've got to behave the way they're supposed to behave, all the original 8 properties from Chapter 2. But in addition to that, if you also have an operation that we'll use triangular brackets to represent, and if that operation satisfies these 4 properties that are just rip-offs of the 4 properties on the previous page, these are just kind of, saying it behaves like the dot product per the 4 properties of the dot product on the previous page. Then now we have a vector space with an additional structure, additional algebraic structure of this operation. We have rules that it has to satisfy. We're going to call that function an inner product. And we're now going to rename this vector space an inner product space. So this term inner product space says it's a vector space and we have an additional operation called an inner product that behaves just like a dot product. And it turns out that with this inner product space, we're going to be able to do some really remarkable things. I'll give you a quick tease. Netflix owes its existence to this idea. And I'll say a couple more words about that next time. All right, see y'all later. Have a good day.